Welcome to The Explainer. Today, we're going to peel back the curtain on something that's happening on your computer, on your phone right now that makes everything just work. We're talking about the secret language of your apps.
So think about this for a second. You do it all the time, right? You copy some text from a website, you flip over to a document, and you paste it in. It's totally second nature. But if you ever actually stopped and wondered, how? How does that even happen?
Because here's the thing. Your web browser and your word processor, they're two completely separate programs. By design, they're isolated from each other, each living in its own little bubble of memory. It's a security thing, it's a stability thing. So, how on earth does that little piece of text jump from one bubble to the other?
Well, there's a secret language at work. There's a whole system, a hidden set of rules and pathways that lets these separate, isolated programs talk to each other. And that communication is what makes your digital life feel so smooth and connected. Now, the official fancy name for this is inter-process communication, or just IPC for short. And really, it's a set of tools that your operating system, Windows, Mac OS, Linux, whatever you're running, provides to let all those different apps and processes chat, share data, and basically work together. I think a really great way to visualize this is to imagine every app on your computer as a separate building. IPC is like the secret network of plumbing and tunnels and messenger routes that connects all of them. It's the invisible infrastructure that lets them cooperate without bumping into each other. And, just like in a real city, you don't just have one way to send a message. You've got mail, you've got phone lines, you've got couriers. Well, the operating system gives your apps a whole toolbox of different ways to communicate, each one perfect for a different kind of job. So here are some of the main tools in that toolbox. You've got things called pipes, sockets, shared memory, message queues, a bunch of different options. Now, for this explainer, we're just going to focus on a few of the most important ones, just so you can really grasp the core ideas. All right, first up is the pipe. It's pretty much the simplest form of IPC you can get. It's just a one-way channel for data. Data goes in one end and comes out the other. Simple. If you want to have a two-way conversation, you just use two pipes.
The perfect analogy for this is one of those old-school pneumatic tube systems, like at a bank drive-thru? You put your data in a canister at one end, and whoosh, it gets sent directly to the other. It's simple, it's direct, and it's really fast.
Okay, next up is shared memory. Now, this is a totally different approach. Instead of sending data from point A to point B, the operating system sets up a special neutral territory, a little patch of memory, and just gives two or more processes access to it. It's a common space. So imagine you've got two programs in separate, locked rooms. But you give both of them a key to a third room, and in that room is a giant whiteboard. One program can go in, write a message on the board, and leave. Then the other program can come in, read the message, maybe even erase it and write back. It's blazing fast because you're not actually moving or copying data around. And let's look at one more, message queues. You can kind of think of this as a mix of the other two. Basically, processes can send little packaged messages to a central queue, which the operating system manages. And the key thing here is that the sender and receiver don't have to be active at the same time. The analogy here is a post office. One program can drop off a letter in another program's mailbox whenever it wants. The recipient program might be busy. It might not even be running. But later, when it's ready, it can just go to its mailbox and pick up any messages that are waiting. It's super flexible. So when you look at these different methods, they really boil down to two main philosophies, two different ways of thinking about communication. You either share a space, like our whiteboard, or you pass messages, like the pneumatic tube or the post office. And this chart breaks it down perfectly. Shared memory, the whiteboard, is all about directly accessing common data. It's wicked fast, but it's usually just for processes on the same computer. Message passing is more like a courier service. It's more structured, sure, but it's way more flexible. It can even work between computers on a network. Okay, so this is all great. We have apps talking to each other, but this creates a whole new problem. With all these conversations happening at once, how do you stop them from talking over each other and just creating total digital chaos? Let's go right back to that whiteboard analogy.
What happens if both programs burst through the door at the exact same millisecond and try to write on the exact same spot on the board? You just get gibberish, right? An unreadable mess? In computing, that's what we call a race condition, and it's a huge problem.
So, to stop this from happening, we need a solution. And that solution is called synchronization. It's basically a set of rules of engagement, a way to coordinate all these processes to make sure they play nice, take turns, and don't corrupt the data.
These are the rules of the road for your data. For example, a semaphore is like a traffic light for a shared resource. A mutex, which is short for mutual exclusion, is even simpler. It's just a one-at-a-time rule for that whiteboard room. A barrier makes a group of processes wait until everyone's arrived before they can move on. They're all just clever ways to manage traffic.
So when you put it all together, the communication methods, the synchronization rules, you get this incredible, unseen engine that is quietly powering almost everything you do on your devices.
But wait, this brings up a really basic question. For two processes to talk, you obviously need two processes. So how does that second one even come into existence in the first place? Well, a lot of the time, one process will actually create another one just to help it out.
In systems like Linux or macOS, this often happens with a system call called fork. And what it does is kind of wild. An existing parent process just makes a call, and the operating system creates an almost identical copy of it, a child process. And from that exact moment on, there are two of them running, ready to use IPC to work together.
And this quote from our source material really just nails it. IPC lets processes talk. Synchronization keeps them from shouting over each other. And you absolutely need both for the kind of parallel, interconnected world we live in today. It's that simple.
So the next time you copy and paste some text or you see a little notification pop up from a background app, you'll know. It's not magic. It's just the secret language of your apps, this constant, beautifully coordinated conversation happening right under the surface. Makes you wonder, what other magic is really just clever communication? Thanks for joining me on The Explainer.